Welcome back, everybody. So today we're going to be talking about something that I think is of kind of fundamental importance for us understanding the limitations of quantum computing and really, in turn, what makes quantum different from classical computing. And this is what we're specifically going to be covering is what's known as the polynomial method, which actually shows some deep connections between the number of queries that you need in order to be able to solve a particular computational problem and the degree of a polynomial that you need to closely approximate that underlying function. So let's begin with this. I just need to load up PowerPoint and spawn some blank slides. All right, wonderful. Let me just now share my screen and we can get started. Okay, cool. So to begin with, let's dive into what we mean by quantum oracles, right? So our goal in quantum oracles, in query complexity, is to understand how expensive a particular algorithm is to run by bounding the number of times that we need to access the input data for that particular problem. So for example, an example we looked at before was the search problem. And basically how the search problem worked is we had some function, some oracular function, f, such that f of x equals 1 if and only if x equals some marked element. And our task in the search problem was to go through and figure out what this value of m was. And we saw that if this function, which if we view it as going from 0, 1 to the n to 1, 0, 1, then the number of times that we needed to query this particular oracle to solve this using amplitude amplification was in order square root 2 to the n. Where here, what this basically ends up meaning is it's an upper bound on the scaling up to constants, etc. So this is what we end up meaning. Now in this, because we're going to be talking about lower bounds, what we would like to do in this one is we'd like to be able to say that that this problem, the search problem, can be solved in using a number of queries that goes like omega 2 to the n. And what we mean here is this is an asymptotic lower bound. And so in this case, the lower bound and the upper bound coincide, which means that the scaling of the number of queries that we need in the best possible case ends up asymptotically going like square root 2 to the n. And we usually write this using Bachmann-Landau notation with a big theta. Okay, so this is what we're going to be ultimately showing. And the way that we're going to be getting there is through the polynomial method. Now, polynomial method isn't designed to solve the search problem or problems like the search problem. Instead, it's used to bound the query complexity for a decision problem. So let me be more specific about this. So if you think the way that a decision problem ends up working is, let's just consider a function f acting on a bunch of bits over here. And what this will do is this will map 0, 1 to the n to some function value. Okay, or sorry, I should say to some function value in 0 and 1 for our particular problem. Okay, so let me just give an example for this. So say we're given a bunch of bits, right? We've got x0, x1 through xn. These are a sequence of bits that could be provided to us through some way or another. We might like to ask a question such as, what's the value of OR of x0, x1, all the way through to xn? All right. This is an example of a decision problem because in this particular case, the OR is always 0 or 1. So another way of phrasing this is that, we say that f of x equals 1 if x has at least one bit equals 1. Now, also, we could think about and as another decision function. And is very similar. And of x equals 1 if and only if x is equal to 1 all the way through to 1. All right, so these are all different types of decision problems associated with it. Another one, for example, is the parity function. The way the parity function ends up working, of course, is that the parity of a particular bit string x is just equal to the sum over I xi mod 2. So, for example, if we take a look at the string 1, 0, 1, 1, 1, this is even and has a parity of 0 because the total number of ones, if we add it up, is 4, which is equal to 0 mod 2. Okay, so those are some examples of functions that are decision functions that we can consider implementing inside this. Now, just to give you an idea about how this relates to the search problem, which we discussed earlier, is we can actually use the search problem inside this framework through the following way. We can envision that these inputs to this or function f of x computes a function on data given by an oracle. So for example, we've got our particular oracle, say for the search problem, where for the search problem we had our oracle function f of x equals 1 if and only if x is equal to some marked entry. Okay, now we can end up seeing our x's for f where as being the following. X0 is equal to the function value at 0. X1 is equal to the function value at 1, going all the way down to f of 2 to the n minus 1 is equal to x 2 to the n minus 1. All right, so this ends up saying that if we want to think about computing a function on all the data provided by the oracle, the value of n, where f, of course, ends up mapping 0, 1 to the n to 0, 1, deciding about this oracle or a property of this oracle, it then would correspond in our cases to a value where n is equal to 2 to the n. Okay, so for all of the cases that we're talking about, because the decision problems that we want to do will be a decision problem on data that's coming from our oracles, for our purposes, this value of n here is going to be 2 to the n because there's going to be a total of 2 to the n possible queries that we can make to our oracle. And the function over here, in principle, just computes a function of any and all of that data that we could provide. And our goal is to figure out what's the minimum number of times we'd have to query this in order to figure out that. So for example, going back to the search problem again, let's look at OR. So asking the problem of how many times we need, computing OR on data provided by the oracle, this is equivalent to asking the problem of, is there a value of m such that f of x is equal to, or f of m equals 1. All right, so basically, the decision problem that we're taking a look at that kind of corresponds to search actually is asking, naturally asking the question of, does there exist a marked element for the search? And can we find it? So that's basically the reason for it. And the reason why we're going to focus on the OR function so much is if OR requires order and the alpha queries, then so too does search. Why is that? Well, the reason why is by searching for a marked element, we can solve the question of, is the OR of all of the possible bits that would be output by the oracle equal to 1, i.e. is there a marked element? And we can figure that out just by searching for the darn thing. So that is the reason why, if we can prove a lower bound on OR, that suffices to prove a lower bound on search. So now we're just going to focus on OR. Now, before we need to get into this, there's a couple of things that we need to discuss, or different types of query complexity. So the symbols that I'm going to refer to is first D of F. This is the deterministic classical query complexity for computing F. Okay, then we have Q 0 F, sorry, QE of F. This is the exact same thing, but using quantum queries. And specifically, in this case, we're going to be assuming queries to a bit oracle. These are the strongest type of queries. With bit oracle queries, we can simulate all the other types of queries that we want. So lower bounding the bit oracle will typically lead to lower bounds for all the rest of the numbers of queries needed. Okay, so then another one that we're going to discuss is Q2 of F, and this is quantum queries. But we're allowed to be wrong at most 1/3 of the time. Now, the value of 1/3, you might wonder, where does that exactly come from? Well, 1/3 comes about because of the Chernoff bound, it turns out. If the probability of failure is less than 1/2, then we can amplify this to 1 minus epsilon for all epsilon greater than 0. So in order, so any constant less than 1/2 would do. Now, just because 1/3 is the simplest fraction that we could end up writing, that's less than 1/2. Typically 1/3 is used just by convention for this fixed number, but it doesn't, the particular choice doesn't matter so long as it's a constant and it's bounded away from 1/2. Okay, so these are the particular functions. Now, the next thing that we want to do is we want to be able to kind of relate the problem of computing this function to actually the problem of approximating the function by a polynomial. And so what do I mean by that? Well, what I mean is, let's consider f of x, which again maps from 0, 1 to the n to 0, 1. we can approximate this discrete function by a continuous polynomial p of x, which will map from, in this particular case, it will map from the reals to the reals. Okay, so just to give you an example, let's consider the OR function. Okay, so I'm going to consider the OR function on 3 bits. So the OR function ends up looking like this. We would have, say, 0 here, 1, 2, 3, 4, 5, 6, and 7. Now the OR function is 1 if at least one of the bits is 1. Now, if we just go through, the truth table of this, we see that, the 1, 0, 1, 1, all the way down to 1, 1, 1. We see that there's only one value when we consider the OR of 3 bits that evaluates to 0, and that's 0. So the discrete function that we would like to build for this, f of x, ends up looking like this. Okay. Now, what we can do is we could always build a polynomial function that maps the reals to those particular values in the following way. We could build it so that it kind of smoothly interpolates between these. So here's an example of a polynomial that we could pick, but of course there's many of them. All right. Now, the key point here is that the polynomial is allowed to be anything it wants at intermediate values, but we constrain this equivalent polynomial at the exact values corresponding to the inputs to agree precisely with this. And for all f of x, there actually always exists a p of x such that p of x minus f of x equals 0 for all x in 0, 1 to the n, or all in positive integer valued inputs, if we view it from the perspective of this line. Okay, fantastic. So now let's go through and show you the construction. The construction is actually pretty straightforward. The proof of this claim is the following, that we just set this polynomial to be of the form sum over y, f of y, sum over k, 1 minus yk minus xk. Okay. Now, the way that this ends up working is that we can just evaluate this polynomial function in the following way. There's 2 cases that we need to consider. One, let's assume that y, which is again the dummy variable of summation in our context, if y is equal to x, and again, this is an n-bit number, so this is in 0, 1, the capital N, then what we end up having is that f of y times the sum over the individual bit values of 1 minus y sub k minus x sub k squared. If they're equal, then x sub k minus y sub k, that's equal to 0 always. Oh, sorry, that is a sum of a product over k. I apologize. So let me go back and fix this. This is a product over k. Okay. So if that's 0, then we end up getting, this is f of y times a product over k of 1, which is equal to f of y. Okay. Second case that we need to take a look at is the case where y is not equal to x. Well, if y is not equal to x, then there must exist a value of k prime such that yk prime is not equal to xk prime, which implies that yk prime minus xk prime absolute value is equal to 1, which implies that 1 minus yk minus xk squared is equal to 0, or k prime, I should say. So therefore, what we end up getting is that there exists one term where this whole thing is 0, if that's the case. And therefore, that result is 0. So it implies that f of y product over k, 1 minus all the rest of this rot, is equal to 0. And this implies then that the sum over y, f of y, 1 minus yk minus xk squared is just simply equal to f of x for all x in 0, 1 to the n. Okay, so this gives us a way of building a particular polynomial of the individual bits of the particular function that we're taking a look at. And we would like to use this the properties of the polynomial to be able to bound the query complexity of computing a particular problem. Okay, so the way that we will do this is that we'll need the concept or the object that the query complexity is related to is the minimum degree polynomial. Needed to interpolate. So just to give you some intuition behind this, let's just consider a case where our function was literally constant, okay? So let's say we had this up here. Our function is just 1 at every single point over here. And so if we had that particular case, well, we can interpolate that this function completely using a degree, well, actually technically a degree 0 polynomial. So we need to provide very little information in order to be able to specify this particular function. We just need a single query, and then that will give us the ability to compute the function value at every single other point. And so you can see that in some sense, right, the minimum degree polynomial that you end up needing kind of ends up giving you actually a notion of how complex the function is that you'd like to compute. And so that's why this notion of the minimum degree approximating function is so important. And so we'll denote the minimum degree polynomial that we need to implement a particular function with 0 error as degree f. And so just to give you an idea, right, the degree of a polynomial is basically the exact same kind of degree that we would see otherwise. It's the highest power of all the terms in it. So for example, imagine we considered the following function. Let's consider 1 minus x1 plus x2 minus x1 times x2. This is a degree 2 polynomial because of the fact that it's got a quadratic term in here. Now, classically, this is kind of a little bit beyond the scope of what we're going to be talking about, but the classical query complexity has been shown to be directly related to this. We have that the classical degree of a function, or sorry, I guess I should say the deterministic query complexity of computing a particular decision function, d of f, this is less than or equal to 2 times the degree of f to the 4th power. And actually, we can compute a approximate version of this the d of f is also upper bounded by twice the approximate degree of the function to the 6th power. Now, the approximate degree of the function, this is the same thing, but we're allowed to have absolute value of p of x minus f of x less than or equal to 1/3 for all x. Okay, so these are two results that end up allowing us to understand, what an upper bound on the minimum query complexity is based on the degrees of these polynomials. And so if we can figure out the degree of the optimal polynomial, then we're good. So that is the other thing that I should note is that because of the fact that this is the approximate degree, it's a weaker assumption than the degree of the exact polynomial. So we always know that the approximate degree of the polynomial, the approximating polynomial for the function f, this is less than or equal to the precise function. Okay, so that is how this ends up working. So in order for us to talk about this a little bit further, I wanted to go into a little bit more detail than I went into this in class. And I wanted to be able to just at least cite some of the main results that can be used in this. So the question is, how do you find the minimum degree polynomial? And in practice, the way that you do this is you use a set of orthogonal polynomials known as Chebyshev polynomials. And these are fantastic because of the fact that they have basically almost all the properties that we want. We can approximate any function using Chebyshev polynomials, and these approximating polynomials are always bounded between -1 and 1, but we can shift it up appropriately, so that way the function can always be between 0 and 1. So Chebyshev polynomials are fantastic because they're bounded and also closely mimic the minimum error polynomial of a given degree. Okay, and it's this property that that Chebyshev polynomials closely mimic it within some bounded error, the optimal polynomial that we can end up getting. This allows us to use the theory of Chebyshev polynomials for us to be able to reason about what the best degree polynomial we could possibly get for a function is. And so this still is a little bit involved, but it's a bit of it becomes a calculation then in polynomial fitting or some reasoning using well-known properties of interpolatory polynomials. But there were some actually kind of broad cases where more or less everything has been solved. And so I want to talk about one of these such broad cases. And in this case, the case that we're going to be talking about here is consider symmetric f. Okay, so this function f is symmetric if and only if f is a function of sum over I xi equals k, I'll call it. Okay, so that is basically the whole idea. So an example of this is OR is a symmetric function. The reason why is that f for the OR function, f of x is equal to 0 if and only if x equals 0. Another way we can write this is that f of x equals 0 if and only if sum over I x sub I equals 0. Okay, so therefore, the function or actually doesn't depend whatsoever on the location of the individual bits. It just depends on the number of ones that we have. If the number of ones that we have is greater than 0, then the function is 1. Otherwise, it's 0. And is also a symmetric function, as is the parity function. Again, they both satisfy the property that the value of the function only depends on the sum of the number of ones that we end up getting in both cases. An example of a function that wouldn't be symmetric would be, let's consider negating one of the bits inside this Boolean circuit. In this particular case, the value of the function that we're computing, the negation of one bit and then the and of that bit with the other one, that function actually depends on which of these two gates that we're knotting, or bits that we're knotting. And so therefore, this is not symmetric. So not all functions are symmetric, but a host of the ones that we're interested in, and in particular the OR function, which is going to be vital, again, for the search problem. So for symmetric functions, there's this theorem that was shown by Parity in 1992. And basically what Parity ends up saying is that for any non-constant and symmetric function f, the approximate degree of the function is lower bounded asymptotically by square root of n minus this function gamma of f over here. Okay. And again, recall that f maps 0, 1 to the n is in n bits to 0 or 1, depending on whether the function like OR evaluates to 0 or 1. Okay, so here gamma of f is equal to the minimum of 2k minus n plus 1, such that g of k not equal to g of k plus 1, where we're assuming, again, k here is the sum over I, xi, so it's just the total number of ones in the particular value of the function, or the input, I should say. And the function g here is defined such that f of x is equal to g of k for a symmetric function. Okay, so this is the result of Parity. And let me just go through it and apply this to the OR function. So OR is an example of a symmetric function, and the function f of x, of course, is equal to 1 in this case, if sum over I, x sub I is greater than 0. So in this particular case, g of k is equal to 0 if k equals 0 and 1 otherwise. This implies that the smallest value of k, such that g of k is not equal to g of k plus 1, is 0. Therefore, gamma of f in our particular case is equal to the absolute value of 0 minus n plus 1 is equal to, oh, sorry, I meant capital N here, n minus 1. Okay, so that is that's the value of gamma. So this theorem, which again is also just proved using the properties of Chebyshev polynomials, this theorem ends up saying that the approximate degree of the function f then asymptotically scales as square root of n. Okay, cool. So now we've got the minimum degree polynomial that we need in order to be able to compute OR. The next thing that we are going to need to demonstrate is that QE is greater than or equal to the approximate degree of f divided by 2. Okay, now the way that we're going to demonstrate this result is unlike the classical results that I stated earlier for the upper bounds. This quantum result, we're actually going to construct ourselves. And the way that we're going to construct it is actually just by considering the form of every possible t-query algorithm. So let's consider a t-query algorithm on n input qubits. So if we have n input qubits over here, then what we end up getting is we end up getting the following, that this function will have n qubits and 0 or 1 qubit here. And then we're going to assume that it will have m junk qubits down here. This is just extra memory that we could use for other purposes in it, but it technically needs to be part of the argument in order to make sure that we don't rule out the possibility that that an algorithm could have done better if we gave it extra memory. So this is just some potentially huge amount of memory that we're giving our t-query algorithm to be able to use for its own purposes. So the way that this general algorithm goes is we'll allow it to do literally any unitary. And then after doing literally any unitary, we're then going to query our black box function. Then we're going to do literally any other unitary. And then we're going to query our black box function. Okay, we'll continue until we end up getting to the end when we're going to do OF and then a final UT over here. So this circuit describes every possible t-query algorithm over here because the U's are allowed to be anything we feel like, including identities in some cases. They could be whatever. So in any case, the first thing that the way that this proof ends up going is we want to show that the states that are generated by this are of the form sum over k, ck, k, where k over here is a degree t polynomial in X. Okay, so that's how we're going to go through it. And the reason why we want to do this is that the probability of k then is a degree 2t polynomial in X. Now, if we want to be able to implement the particular function, in this case, this function, is the OR function. But if we want to be able to implement this using the minimum degree approximating polynomial, we need to make sure that we nail it at every single point. So the idea then is that if we don't have a high enough degree in our function, in order to be able to match the function at each of the interpolation points, which are values like 0, 1, 2, all the way down to n minus 1. So if we don't have a high enough degree polynomial to be able to match it, then we know that this function, or that t queries, is not going to be sufficient. Now, if we match it, then we still might not be able to actually achieve this lower bound. However, if we're not capable of matching the degree of this distribution in probability, then we're not going to be able to do it. So this is what justifies that claim, why it's over 2, because going from a degree t polynomial to a probability distribution ends up giving us a factor of 2 because, well, it's squared, right? And so that's where the 2 comes from over here. The main thing that we need to justify is this claim I made that the c sub k's are a degree k polynomial in X. So let's go through and validate that. So the simplest case that we can consider is imagine one query. So if we've got a one query algorithm, we can begin without loss of generality in a state 0n, tensored with 0, and all the rest of the junk qubits. After an application of an arbitrary unitary, this will end up producing a state ILJ, CILJ for some constant CILJ, ILJ. Okay, and then this is the action of the first unitary in this canonical circuit over here. So we've just done this guy. Now we're going to apply our black box oracle to this. This will give us sum over I and j, ci 0j, I, f of I, plus ci 1j, I, f of I, exclusive or 1, all, or sorry, not ket there, exclusive or 1, all tensored with j over here. Now, what we can do is, because this is a Boolean function, right, there's only two possibilities for f. Either f is 0 or f is 1. So we can break this up into the two possible cases by writing this as sum over I, j, c sub I, 0, j, times, let me just make sure that I get this right, times 1 minus xi plus ci 1j xi times I 0 j plus ci 0 j xi plus ci 1j 1 minus xi I 1j. So why did I do this? Well, the reason why I did this is I said, okay, well, let's expand this out over here. Now, we have two cases. Either f of I is 0 or it's 1. We've broken it up into those cases. Okay, now if f of I is 0, then f of I, of course, using our other notation, is equal to xi, because x is the vector of oracle evaluations. Okay, so f of I is xi. So if if f of I is 1, then this would be 1 over here, and C10's coefficient would be 0, matching this up here, because if it's 1, then it shouldn't have a 0 coefficient. On the other hand, if f of I is 1, then f of I exclusive or 1 will be 0, and thus it'll give us this coefficient over here. So you can see that since there's only two cases, x of I equals 0 or x of I equals 1, in both cases, we end up getting the same pattern that we see up here. And similarly down there, we see the same thing. Therefore, we end up getting the fact that all one query algorithms, the output state from them can be written in the form sum over k, ck, k, where this is a degree 1 polynomial. Okay, and so that is that, and the reason why it's degree 1 is because all of these terms that we're multiplying the constants by, the ci0j's, are all themselves polynomials. Okay, cool. So then actually, once we've got this, it's straightforward to end up creating an inductive argument. And just to give the kind of sketch of how the inductive argument ends up going, what we do is we assume that we start with ci0j being a degree p polynomial. We apply a unitary to it. A unitary is going to take ci0j and it's going to sum together all the coefficients. But because of the fact that the unitary transformation just leads to a sum of all of those different coefficients, this is going to lead to a different distribution of cilj's that are all going to also be of degree p, because the sum of polynomials doesn't change the degree of the underlying polynomials. And a unitary transformation, it just sums together all of the elements that it's acting on with different weights. So therefore, we have a degree polynomial. Carrying out the exact same argument that we ended up giving here will yield a degree p+1 polynomial, because this, the ci1j, for example, is now going to be degree p, and we're multiplying it by x, so this will go to degree p+1. And that is how the induction step ends up going. And so therefore, the c sub k's are a degree t polynomial for any t-query algorithm. And so this ends up kind of concluding with our statement. So this, and using this result, that the deterministic query complexity is less than or equal to is greater than or equal to the degree of the function divided by 2, we end up getting that this implies that the deterministic quantum query complexity is greater than or equal to square root of n over 2, because we used this theorem from Parity that because OR is a symmetric function, OR can be computed in square root n time. Therefore, it's just a deterministic query complexity is square root n, which, because n is the total number of queries that we can end up making to our oracle, this is root 2 to the n. Okay. Similarly, the exact same arguments actually end up going for and. If and is also a symmetric function, and that it has the same degree lower bound, and so if we wanted to compute and, it's also in omega root 2 to the n. So asymptotically speaking, and or on quantum computers have exactly the same lower bound. Parity, on the other hand, parity is interesting. If we go back to that Parity result, Parity ends up saying, okay, well, what is this gamma function over here is the minimum over 2k minus n plus 1, such that g of k is not equal to g of k plus 1. Now with parity, what we have is that the parity is a weird function because of the fact that if we have k equals 0, then this is even. K equals 1, this is odd. K equals 2 is even parity, where k again is just the sum over I xi's. So that, for example, the k equals 2 strings might look like 1, 0, 0, 1, something like that. So parity always ends up flipping. So the distance between the function values that are evaluate to 0 and evaluate to 1 is always 1 for parity. So using that Paturi result, this ends up implying that gamma of f is actually equal to 1. And this implies using that theorem that the approximate degree of the function is then greater than or equal to square root of n minus 1, which is asymptotically equal to omega of n. So this is really fascinating because what it says is it says that parity is an example of a function where we get no quantum advantage asymptotically. Quantumly, we have to look at all the bits in order to be able to learn what parity is. Whereas computing the OR function or AND function, we only need to look at square root of the number of bits. So this is a great indication that actually quantum doesn't actually always even give us polynomial speedups or problems. For parity, best we can end up getting is a constant factor. In fact, the factor of 2 that's suggested by the polynomial lower bound actually is optimal. So that is the that's parity in a nutshell. And this ends up, of course, leading us to our final conclusion, right? Or requires square root of 2 to the n oracle calls to find the OR of all bits yielded by the oracle function f, okay? And this is equivalent, solving this problem is equivalent to determining whether a marked state exists. This problem can be solved using search in time square root 2 to the n. And so therefore, because of the fact that search reduces to this, if we could perform a calculation of the OR of all of the bits faster than, if we could perform a search faster than the time it was required to do an OR, then we could use the search in order to compute the OR and create a contradiction. And so that's what ends up leading us to conclude that search, therefore, because we can use it to compute OR, has to be in omega square root 2 to the n, okay? And that is the final result. Now, the last thing that I wanted to mention is, well, what about those classical bounds that I gave before? Well, from the classical bounds, actually, one of the things that we can end up saying is we can actually go through and use these results that we end up getting in order to be able to bound what the best ratio of the quantum complexities or query complexities will end up being for any decision problem like this. And so we end up finding, actually, just by using those results, that the error-free quantum query complexity actually is upper bounded by the deterministic query complexity divided by 32 to the 1/4. And this is just actually using the fact that this is lower bounded by df over, by the degree of the function divided by 2. And so by substituting that into those classical upper bounds that we ended up getting and isolating, we end up finding that the best case scenario that we can hope for a deterministic quantum algorithm for solving a particular decision problem is at best a fourth root reduction compared to the classical runtime. So that means that for most of the problems that you know and love that can be phrased as a decision problem, the speedups that quantum computing can offer, at least in a query model, are actually relatively modest. They're not exponential separations like we ended up seeing for problems like the Bernstein-Vazirani algorithm. Instead, actually, we can only usually hope for a fourth root speedup, which is pretty substantial, but is more typically the speedups that we tend to get are quadratic in nature. So we tend to get more like square roots coming back out of it. So that's an important limitation to pay attention to. But one of the other ones that's very important that we end up getting is a parity lower bound. We'll see that this parity lower bound is very important because this places limitations on how fast quantum computers can simulate quantum dynamics through what's known as the no fast forwarding theorem. And we'll get to that later. But the key thing that I wanted, that I hope that you get out of this is that quantum computers in a query model do not provide exponential speedups for absolutely everything. Often polynomial is the best that you can do. And that something that you should always think about when you're designing a quantum algorithm is you should ask yourself, well, can I provide a lower bound on my algorithm by reducing it to some problem like parity or search / computing the OR function? And if you can do such a reduction, then that actually can help you a lot because it will allow you to understand how close to optimal your quantum algorithm actually is without needing to go through all of the sophisticated machinery of directly proving a lower bound using a method like the polynomial method. Well, thank you very much, everybody, and see you around next time.